Hello everyone, I'm Yuri from the Hackathon Team 7 and I'm going to present to you the solution that me and Michał came up with. We start by loading and looking at the data, policyholders first. We will be calling them users moving forward. There are lots of null values for streets and house numbers. Gladly, Azure API can compute routes between let-long pairs. During this stage of the project, it's really important to understand your data very well. We can see that villages and village parts are filled for every user and they already represent clusters of users, so we may use them for routing optimizations in the future. Also, we can use street info to better approximate driving distances and times for each individual user. Now let's look at the clinics. We see that a lot of clinics, presumably 14K, share the location. This is not surprising, given that each individual row in the table represents an individual clinic department. But we will continue to call them clinics for convenience. Missing streets shouldn't be a big deal, since we can calculate distances using let-long and those filled in for every clinic. We also notice that a lot of clinics miss department ID and contractual specialty ID. If we will drop that data, we are going to ignore 6K of the clinics, and that's a lot. Department ID and contractual specialty ID have the same amount of null values. Let's check whether they're always missing together. They do. Let's see what we can do to fill nulls in. Maybe the map of the clinics will give us some insights. Neither the map nor the online research we did helped us to fill in the missing data. Given that department and specialty IDs are essential for the task, we will have to drop the clinics that miss them. A room for improvement lies within properly filling that data. Let's move on to the ambulance stations. Streets are missing for some ambulance stations, but that's okay since we can calculate routing distance based on let-long. We've dropped all clinics that miss contractual specialties, combined clinics and ambulance stations in a single orgs table by treating ambulance stations as orgs of a special type, and grouped them by their exact location. That left us with 11K of the actual clinics that we will be computing routes to. From the start, we've aimed for the maximum precision. And obviously, the most precise way to solve the task will be to compute distances for each user individually. So we've implemented this straightforward solution first to identify the slowest part and work from it. Turned out that the slowest part is, not surprisingly, routing, and we will have to optimize that, using some kind of user and maybe clinic clustering. The most difficult part of the task is to find performance solution without sacrificing much of the precision. Let's return to the data exploration and plot parent orgs at users. Let us also explore Voronoi regions of different types of clinics as an option to quickly query candidates. As you can see, some clinics have very sparse coverage. If they represent an important specialty, there needed to be more of them. And finally, let's compute clusters for villages, districts, and radiuses of 500 meters. These 47K radius clusters seem like the way to go for the efficient and precise solution. With $200 of MS Azure credit, we are able to run only 40K queries against the routing API if you want to send more than 50 of them per second. And with 47K clusters, we will definitely need to send more than 40K requests. To not sacrifice the precision and to be able to iterate quickly, we set up a local instance of the OpenStreet routing machine. Based on the measurements above, let us use Haversine distance for any of the straight line distance computations instead of the true geodesic Vincenti distance, despite it being less precise for geodesic computations. We can do that because we could compute Haversine distances much faster, and error margin it reduces is not significant on a scale that we work with, and we only need this distance for approximations. The solution is quite straightforward from that point on and consists of the following parts. Creating a vectorized method for selecting clinic candidates for individual clusters based on the straight line distance. Creating a method to find solutions for each of the clusters. To be performant, we look for all types of clinics in a single pass over a sorted list of candidates. It's hard to vectorize it, so we run it in multiple threads. Notice that the solution incorporates our knowledge of the fact that there are some clinics of the same time that share the same location. When we encounter this, we randomly distribute users between such clinics to provide better coverage. And finally, we have to run this algorithm on all of the clusters. Running the solution on 47K clusters took 3 hours and 40 minutes. The result we are quite happy with. Then we have to write it to the output CSV, and because we really care about precision, we will adjust distance and driving times for each individual user based on the ratio between user to clinic and cluster centroid to clinic straight line distances. As you can see, we came up with an elegant, efficient, and precise solution by thoroughly analyzing the data, clustering the users, setting up the local routing machine, vectorizing and parallelizing the computations, and approximating final driving distances and times for each of the users individually. Now I will pass the mic to my brilliant teammate Michał, who will present to you our results in a SAS VIA dashboard. Bye.
Hello everyone. I'm Michał and I would like to present you an interactive dashboard that Yuri and I have created for this hackathon. In order to make this demo quick and performant, we used only a subset of whole generated data that contains around 700 randomly selected inhabitants of Prague city and their corresponding closest clinics and ambulance stations. Input data with Prague patients has been joined with 3 tables that we got from organizers in order to get full metadata. That join has been done with tools available in the Prepare Data section. Data has been enhanced with a bunch of custom data items like geography items or aggregated measure items that were used as a source data of dashboard objects. Okay, so let's look at the dashboard itself. This dashboard is composed of 5 pages that can be grouped into 3 parent categories called clinics per users, stations per users, and users per clinics per stations. On this page, you can learn about the distribution of specialties and users across different clinics. This is a fixed page with only a brief overview of underlying data. The real fun happens on the next page. Here, you can get detailed information about clinics and their coverage. All objects on that page are connected with two-way filter action, so they update automatically as dashboard user goes through particular clinics. You can filter clinics by typing the name of the organization, by selecting the clinic ID, or by selecting a specialty ID of that clinic. You can also just select clinics on the left side map. When you do that, the map on the right side refreshes with all patients that are assigned to that specific clinics. You can also see that there is additional metadata on the left side map with number of users assigned to each clinic and its contractual specialty ID and name of the organization. Two next pages with station user patient section have been created in the same style. There is a fixed page with ambulance station statistics and interactive maps that allows user to get more data about ambulance stations. It works basically in the same way as the previous interactive maps. The last page is another map-based exploration page that we are already familiar with. In this page, however, the roles are reversed and you can focus on a specific user, selecting him by its city, village, name of the street or house number. You can also again select that user on the map. Let's try to do that. Once you do that, you will get information about all clinics assigned to that users with their distances and travel times. And also an information about ambulance stations that got assigned to that user. This is all. I really hope you enjoyed it. Thank you for organizing this event and have a great day.